we have missed 1 billion years of Earth's history. How could such a significant part of our planet's past vanish? What secrets lie hidden within this gap? This is the story of the Great Unconformity, one of the most intriguing and mysterious features in Earth's geological record. What is the Great Unconformity? And why is it so mysterious? The Great Unconformity refers to a massive gap in the geological record where younger sedimentary rocks rest directly atop much older igneous or metamorphic rocks with no intermediate layers to show the time in between. This means that millions to over 1 billion years of Earth's history are unaccounted for in the rock layers. The Great Unconformity represents a gap in Earth's geological record that ranges from millions to over 1 billion years depending on the location. In some areas, the missing time is closer to 500 million years, while in others, it exceeds 1.2 billion years. It's like opening a book only to discover that entire chapters have been ripped out, chapters that could reveal critical moments in the planet's history. How did this gap form? The most widely accepted explanation is that massive erosion during ancient times removed entire layers of rock. But what could cause such extreme erosion? One possibility is that tectonic forces uplifted entire regions, exposing them to the relentless forces of wind, water, and ice. Over millions of years, these forces wore away the upper layers of rock, leaving the ancient basement rocks exposed. When the land was eventually submerged again, new sedimentary rocks were deposited on top of these older surfaces, creating unconformity. Some scientists suggest that these snowball Earth periods, when the planet was almost entirely covered in ice, played a major role. During these global glaciations, massive ice sheets could have scraped away surface rocks, much like modern glaciers carve valleys today. Why is the Great Unconformity important to understanding Earth's history? This gap often aligns with periods of major geological upheaval, such as the formation and breakup of supercontinents like Rodinia. For example, as continents collided, mountain ranges formed and eroded, likely contributing to the removal of vast quantities of rock. The missing record might hold clues about how these supercontinents shaped the environment and influenced early life. Could the Great Unconformity be connected to the Cambrian explosion? Fascinatingly, this massive time gap often predates the Cambrian explosion, a period around 541 million years ago when complex life forms suddenly flourished. Some researchers think that the erosion and tectonic activity associated with the unconformity might have released nutrients into the oceans, creating conditions favorable for life to thrive. What tools do scientists use to study the Great Unconformity? To unravel this mystery, geologists analyze the rocks above and below the unconformity. Techniques like radiometric dating help determine the ages of these rocks, providing a timeline for when the missing layers might have formed and eroded. By studying these boundaries, researchers can piece together a partial picture of what might have happened during this lost time. Could other planets have their own great unconformities? Interestingly, scientists have observed features on Mars that resemble unconformities, suggesting that similar processes of erosion and deposition occurred on the red planet. What does the Great Unconformity tell us about the fragility of the geological record? The fact that so much of Earth's history can simply vanish reminds us that the rock record is not complete. It is a fragmented archive, subject to the forces of nature. What role do tectonic forces play in erasing geological history? The movement of Earth's plates generates incredible stress on the crust, which can lead to large-scale deformation. Imagine mountain ranges forming and then eroding over millions of years, their remains scattered across ancient oceans. How do scientists reconstruct events from the fragments left behind? It's like piecing together a jigsaw puzzle with most of the pieces missing. For example, chemical signatures within the rocks, such as isotopes of oxygen and carbon, can provide indirect clues about ancient climates. Fossilized microorganisms found near unconformity boundaries might also offer hints about life's evolution during the missing eras. What more could these fragments reveal if we had the full picture? Earth's surface is a dynamic, ever-changing environment shaped by countless processes working over immense timescales. Was it one singular event, like global glaciation, or a combination of factors, including erosion, tectonics, and climate shifts? Scientists debate these possibilities, each new discovery adding another layer of complexity to the story. Could human activity today leave a similar unconformity for future scientists? It's a chilling thought. Rapid urbanization, mining, and deforestation are transforming Earth's surface at unprecedented rates. Could these changes create gaps in the rock record that will puzzle geologists millions of years from now? If so, what story will those gaps tell about humanity's impact on the planet? What lessons does the Great Unconformity offer for our understanding of Earth's future? The forces that shaped this billion-year mystery are still at work today. As continents drift, glaciers retreat, and oceans rise, the geological record continues to evolve. Understanding the Great Unconformity isn't just about solving an ancient puzzle. It's also about recognizing the fragile, interconnected systems that define our planet. As we uncover more about the Great Unconformity, we are left with as many questions as answers. How did these missing chapters shape the world we know today? What role did they play in the rise of life? And most importantly, what lessons can we learn from this billion-year mystery? The Great Unconformity challenges us to think deeply about the forces that have shaped our planet and the hidden histories waiting to be discovered.